can indeed do that. Tell you a little bit about LIBOR. I will make a connection for you later on. As an experimentalist, it's like a little technical detail that really gets you on in the lab, right? It's like a very small thing in the end, how that connects between LIBOR MOT and KRb work. But I just want to make that connection. So as we have all heard about making a MOT for molecules, all about plugging all the leaks. There's vibrational leaks, there's rotational leaks, there's hyperfine, and so on, dark states, lots of stuff going on. And this is not to bore you with all the energy level structure, except to point out to plug a rotational leak, you have to drive from delta N equals to -1. And this is the conventional so-called type 1 versus type 2 MOT. Type 1 MOT, where you have upper manifold has more angular momentum components than in the ground state, therefore you can do this MOT without worrying about getting into the dark state. The type 2, because of this particular requirement of a rotational closure, you have more angular momentum in the ground state than the excited state. So as soon as you try to build a MOT along this, there will be a dark state forming because you have angular momentum states down here that can the molecule will be pumped into. Sorry. Is it on? It's good. And so this is the problem. And in the early days, when we pointed out you need to break the dark states, and in fact, the very first MOT, DC MOT, that was realized in Dave's group, and later on also Mike Tarbert helped analyze it, is that if you had non-zero magnetic G factors in the excited state, it turns out as the molecules move around in a inhomogeneous magnetic field gradient, you can experience different excited state manifolds gets into resonance with the dark state, and you actually can break up the dark states. And this happened to work. But if you have a molecule which doesn't have non-zero G, there are two techniques to break that dark state. For example, you can switch the polarization back and forth, which is one way of breaking the dark state. Along with that, you have to switch the magnetic field with it. So if you're synchronously switching the polarization of the laser field coming into making a MOT, as well as the magnetic field that's forming the quadrupole field for the MOT, you can actually make a so-called RF MOT because we're actually switching this as fast as optical pumping rates, which is at a few megahertz. So this is a radio frequency switching of the magnetic field using resonant tank circuits. Another technique that was proposed by Mike Tarbert is, instead of using opposite polarization, opposite magnetic field switching really fast, what if we have opposite polarization and opposite detuning? So you can have a red detuned laser and a blue detuned laser. All you need is to make sure those are addressing the different MF manifolds with different opposite polarization. And that can also break the dark states. So this is a dual frequency DC MOT was proposed back in 2015. Now can be realized in the MOT for molecules. And I think this triggered Mike to think about the so-called blue-detuned MOT. This was actually never been done before, even in the atom MOT case. This was a proposal. But before we talk about blue MOT, it's really interesting to talk about gray molasses because that's actually the connection to KRb. What gray molasses, this is not a really new concept. It's an idea dating back to the early days of surface cooling and so on back in the 1990s. But I think, for example, this was actually Ted Hensch's group that demonstrated gray molasses in the 90s. Mike Tarbert reanalyzed it in the form of the molecular cooling. But if you think about it, it's actually a very simple idea. If you have a laser that's detuned, for example, blue to the excited state, then you know the AC stock shift pushes its energy states up to the ground up. In the red detuning, pushes down. So in this case, when you have more manifolds, more angular momentum components in the ground state, the molecules gets pumped into the so-called dark state, right? When you are in the dark state, it moves along without experiencing the potential. So if the molecule is moving really slowly, it will remain in the dark state. But as soon as it moves a little too fast, it can get into, by the non-adiabatic transition, into a bright state. Molecules just moving too fast, and it cannot follow the field in the MOT region. Once it gets into the bright state, now because it's a blue detuned laser, the energy shift is up for the ground state. So now the molecule starts to climb the hill. By the time it reaches the brightest laser spot of the standing wave, this is where the most likelihood for this molecule to be optically pumped into the excited state and then lose energy back down. So by doing this process, just like a surface cooling, you get the molecules cool down by doing the blue detuning. And you can see for the red detuning, it actually leads to heating. Okay, so this is the so-called gray molasses. And what Mike brought into this picture is, he said, well, if the excited state has a big enough G factors, you can actually see that the gray molasses can work. At the same time, you can also have restoring force also working. And that's the component of the so-called blue-detuned MOT. The idea being, as a molecule is being pumped into, for example, more stretched states, because of the G factors large enough that the molecule can be driven into smaller magnetic field region while maintaining resonance with the laser field. So if you set the polarization right with respect to the G sign of the G, and if the G of the upper state is big enough, you can actually get a restoring force working as well as the gray molasses for cooling. Okay, so this is the basic idea. And in fact, I think Mike's group tried for calcium fluoride. The G factor is a little small. YO, the molecule we have been working in JILA, has a factor of 3 larger G factors. And indeed, the Mike's group actually demonstrated this blue-detuned MOT for rubidium atoms last year. And we can now actually make that idea work for the YO. And even more exciting is that, of course, if the gray molasses works on dark states, then what if you introduce another manifold of the hyperfine states in the ground by just coupling them with 2 different lasers? And this was an idea that was also early on demonstrated by Christoph Salomon's group for atoms. And John Doyle's group last year have been demonstrating this for imaging of molecules and so on, use lambda-enhanced gray molasses cooling. The idea is extremely simple. Instead of using the dark states coming from one manifold of hyperfine states, you can use laser field to couple another manifold. You can use more laser field to couple more if you like. And the more of those, the more dark states you're providing. And in fact, laser cooling is working on this transition, for example. So you have typically big laser field here, a small laser field there. So most of the dark states residing in this particular manifold. And laser cooling, in fact, can be working with most of the molecules sitting in the dark state. And only when they break the dark state, they will be laser cooled. Very much similar to the early ideas for cloud continuity of VSCPT. And fortunately in YO, the bigger the splitting of data, the more robust of this dark state. Because you can think of, if the splitting is really large, they are forming dark state, and this one is very far detuned from that state by delta, such that it's no longer doing very much incoherent optical pumping. So the bigger the delta, the better, as long as you can make those lasers to be phase coherent. So this goes with, pretty much following what Mike Tubbett has been proposed. Dual frequency DC MOT for YO, and it gets to millikelvin or so. You turn on blue-detuned MOT, lots of laser manipulations along the way, and you do gray molasses, enhanced molasses, lambda-enhanced gray molasses, 40 microkelvin. And this is actually unoptimized. This was just very recent. And so we are going on, in YO also has a narrow line. So we're very excited of getting this molecule to microkelvin temperature. But the point is, it's not to demonstrate YO for a 2D quantum gas, really is to show that this idea of very simple gray molasses plays a big role in laser cooling and making a magneto-optical trap. But the same idea will have, turns out, had a big impact for KRb molecules. So now let me switch to the KRb molecule. It's totally different technology now. We started with atomic species of fermions and bosons. And this goes back more than 10 years ago. Our chair was a graduate student leading this effort. And the idea being bring those atoms together through Feshbach resonance and through coherent transfer between a pair of Raman beams, you can create ground state molecules. And this technique has been used now in many other places, in Durham, MIT, Hong Kong, Innsbruck, and so on, creating molecules near quantum degeneracy, not quite at the quantum degeneracy, but close enough. In this particular case, from 10 years ago, we have Fermi temperature to be above 1.3 times the Fermi temperature. And dial forward for 10 years, this is the second generation machine in the JILA for KRb. And actually, in fact, if you look at this cell, we have all the electrodes now inside the vacuum that can support fairly large electric field. And hopefully that we are just experimenting now that we can move molecules around in this region and figuring out all the electric field gradient and the field strength to really be able to realize this fully polarizable dipolar gas there. We also implemented a high imaging resolution, which so far we haven't used it, but in principle we'll be able to achieve a few optical lattice sites, and the overall system looks like that. But the connection that the detour I made with YO, it really is this gray molasses idea. Such a simple idea that's been there for a long time. We just didn't use it for atomic species until about 2 years ago. And it actually turns out it's very easy to implement. As we talked about, in atoms it's actually even easier because those hyperfine structures can be connected with phase coherent sidebands through EOM, AOMs. And you can very quickly implement for both rubidium and potassium. Each species increase the phase space density by 3 or 4. Altogether, that's a big factor. Okay, so the idea is to try to cool the atomic species of a fermion, potassium, and a bosons deep into the quantum degeneracy. And before, we were not able to go very far below because potassium is a single component fermions. When temperature gets really low, the evaporation loses power. So all the cooling of potassium is done through sympathetic cooling with BEC, with a boson, with rubidium. But then when the boson numbers gets limited, and if the potassium still has a large quantity left and it's very hot, it's very difficult to cool them down, right? So this seemingly very simple technical trick plays a big role. And the reason why I say that is, as soon as we did this, Luigi is sitting in the audience, Giacomo is sitting in the audience, they were the ones who implement those in the lab. And as you can see now, we can create dual species well below degeneracy, where T over TF for potassium can be 0.1. And before we were able to only get to T over TF of 0.3, 0.4. And that factor of 3 or 4 makes a big difference. And the rubidium BEC can get to T over TC 0.5. And as you can see, you can actually vary quite wide range of temperatures and atom numbers to go to very different spaces of phase space density here. So with that, you can actually immediately create KRb molecules that with a range of T over TF. The KRb molecule will be fermion because you're pairing up a boson with a fermion. The lowest temperature for KRb Fermi gas is at 0.2 or so. And we can actually create 30,000 molecules at a T over TF 0.3 or 100,000 molecules at a T over TF of 1.0. And so these are a large number of molecules we create. And all of that is because of this factor of 3 or 4 gain in phase space density for each species. And so when the temperature of a T over TF gets lower and lower, the fresh bulk conversion efficiency gets better and better. And the reason is because previously when we convert a KRb into a rubidium potassium into a KRb molecules, the fresh bulk conversion efficiency is limited by 3 body loss. The remaining rubidium loves to come in to interact with the KRb fresh bulk molecule because when KRb is still a fresh bulk molecule, the rubidium still retains its bosonic character. Another rubidium comes in, they love to get together and collide. And so anything that's not converting this rubidium BEC into a KRb molecule is a potential threat to a KRb molecule. But with going down to very low T over TF, say 0.1 for potassium, we have now more than 50% of rubidium gets converted into the molecules. And this is the conversion efficiency of fresh bulk molecules as a function of the Fermi temperature of the potassium gas, which is, this is kind of like a positive feedback. As soon as the temperature is lower enough, the phase space density overlap between the two species gets better and better. You have more and more higher efficiency to convert all of your rubidium atoms into molecules. Ideally, you have this BEC sitting under this giant Fermi C of potassium. At the bottom, rubidium is the minority. And if you have a conversion efficiency high enough, every single rubidium atom gets converted into KRb molecules, and there's nothing left for the rubidium to destroy KRb. So as you cool this further down to lower T over TF, you get actually better in terms of the conversion efficiency. And this is really all works in this kind of a positive feedback. So a very small trick of gray molasses at the beginning, gaining factor of 3 or 4, plays big dividends later. When we create, these are just the small tricks. Again, when you make molecules, initially the dipole trap is of course tilted with gravity, and this is the molecules, atom sitting in the for potassium in a dipole trap, in the same dipole trap, rubidium and the KRb, they all have a slight different polarizability and a mass. So they have a slight different sag. As soon as you make KRb molecules, because now it's created from non-equilibrium position from the KRb, potassium and rubidium atoms, you can see the potassium atom, KRb molecules start to oscillate back and forth, which is sort of a dipolar oscillations, center of mass oscillations in this trap. And if you don't solve that problem, they quickly heat up, and the heating leads to loss. So we want to remove this so-called slosh heating as quickly as possible. And all we did is just add a very small corrugated potential along the way, and it very quickly dampens this the motion out. And that gets molecule cold and stays there. We can do a very quick molecular momentum distribution measurement. Here's a Fermi distribution, and you look by momentum expansion in free space. You can look at the momentum distribution as a function of the free flight time. And here's a fit with the Fermi Dirac function, and you can see the residual looks pretty good. If you try to fit it with a classical Gaussian function, it deviates away from that classical behavior. And if you try to fit only the wings of the thermal wings of the momentum, you can clearly see by the center, it grossly disagree with the distribution of the molecules in Fermi gas. And so from these measurements, we determine the Fermi temperature of this molecular gas. So with that in hand, we want to go back to look at some of the studies we did 10 years ago. One of those is the so-called bimolecular reactions. And at the time, this was actually very easily explained by the fact that when two KRb molecules come together, they will have exothermic chemical reactions, rubidium to potassium 2 is coming out. And we are going to hear exciting talk from Ming Wang in this workshop. In fact, they have now detected those species. This is just really completing this very nice story. But at the time, we didn't know that were those species, but we made a postulate. This must be what's happening because KRb was cooled down to the ground state. And yet the molecule is being lost with this, following this two-body loss rate. And if you plot this as a function of temperature, you can see the loss rate, regardless of what different hyperfine states you pick, is always proportional to temperature T in this so-called P-wave threshold regime. And the explanation was very simply provided by Paul Julian, John Bone, and so on, saying that it's all long-range physics, where for P-wave interactions, you have angular momentum equals to 1. And that's because the fermions cannot collide with S-wave. And so you have this little centrifugal barrier, which is 24 microkelvin. The molecules coming together at a few hundreds of nanokelvin. So it's below the barrier. You have to tunnel behind the barrier. And then you can calculate the threshold behavior as proportional to T, and you can see beautifully fit. This is actually a fit, but their theory is right on top of each other. If you remove the barrier, for example, just by flipping the nuclear spin such that these molecules are distinguishable, they can come together with S-wave, that barrier goes away, and the rate goes up by a factor of 100 and loses temperature dependence. So if we look at this behavior again now, where this is the past result that's summarized here. Actually, in fact, the MQDT, this is a theory that multi-channel quantum defect theory that Paul Julian and so on put together. The experimental results at the time was a little bit higher above the theory. We revisit those measurements now that T over TF is much less than 1. And the same red curve actually is this, because this is a semi-log plot. So this is the same linear curve that was showing here. And you can see this data, there are two groups of data. There's a group of data which sits at T over TF greater than 0.6. Those are marked by red. And the T over TF less than 0.6, those are the points sitting by in the blue. You may ask how come that you have, near the same temperature, 400 nanokelvin, you have a points which one is greater than 0.6, the other one is less than 0.6. That simply reflects the atom molecule number is very different. This one has a lot more molecule numbers, so that TF is lower. And you can actually see for for classical gas, we pretty much recover the classical prediction of beta over T equals 2.8. That's the MQDT theory predicted. The rate constant is proportional to T with that proportional constant in front of it. But for Fermi gas, when T over TF is less than 0.6, there's a suppression of the reaction rate. Where does that suppression come from? And we can actually normalize this as a function of temperature. You can just, instead of plotting beta as a function of T, you can divide the beta by T. And then this looks like exactly like the 0.6 where Fermi degeneracy sets in. You have a T of beta over T essentially equals to constant, is predicted by classical MQDT theory. Below T over TF 0.6, this starts to be suppressed. And this was, the data was analyzed just simply as, dN dt equals to the minus beta n squared. It's the rate coefficient describing the loss of the two-body process. N is the average density that we measured in this Fermi gas. So Anna Maria Ray has now come up with a theory to explain this. Turns out it's actually two mechanisms working together to explain this suppression. We just have to remember when temperature goes to 0 for a Fermi gas, energy is finite, right? This is a Fermi surface. This is the Fermi energy. That's the second fact is when temperature goes to 0, the volume of Fermi gas is finite. It cannot collapse. It's unlike BEC that collapses. Third is actually a very interesting point that the heating rate actually plays an important role. The heating rate is not just the heating rate that people typically associated with so-called anti-evaporation, where if you have a two-body process going on, you tend to have where the densest part of the sample will have the biggest loss. So this is so-called anti-evaporation in the sense that this two-body loss process preferentially removes molecules from the lowest possible trap depth, the coldest spot. But turns out that heating rate itself is not enough to explain. What we experimentally observe is actually slightly higher heating rate in the sense of the molecules, when they break apart, as they move out, they actually collide with the very dense samples of molecules sitting there. And in that process, they actually heat up the quantum gas. This is the same effect Valad and Vuletic now have seen for both BEC and for fermion. There's always this heating effect where you have loss process going on. The molecules cannot just be plugged away saying, oh, there's a two-body loss, and they are disappearing into the vacuum. They have to move out of the gas, and during this process of moving out, they collide with the remaining molecules and heats up. So that's the H that we can actually measure in the experiment. If you put all these three things together, through some mathematics Anna Maria has done, you can see the beta is actually, the first term is a classical. The volume is just two-body particle loss rate. And you can see they are related to the two-particle density loss rate through this volume normalization factor. But more importantly, there's this quantum correction term. And when you're above the Fermi degeneracy, the energy of the gas equals to 3 kBt. So this term vanishes. There is no extra suppression. But when temperature goes below T over TF, then this term becomes much bigger because the energy remains finite. So this term becomes much bigger. Of course, you can say, well, can you get beta into the negative term such that you start to create molecules instead of losing? Of course, that's not going to happen, right? There's a higher order terms that's going to suppress it. But just the leading order term, you can see clearly that as you go below the degeneracy, this term multiplied by this heating rate is actually what's contributing to the loss of suppression of the two-body loss. Okay, so in fact, they have done numerical simulations based on that model and now have a qualitative agreement with experimental measurements to explain this suppression of the loss in the quantum regime. So the next goal, as I promised, is talk about towards 2D Fermi gas. The goal is really to be able to create Fermi gas in a two-dimensional space. And ideally, you would create bilayer or trilayer molecules where you can have a dipolar interactions between the, each layer represents an independent Fermi C, And with electrical field applied, you can have a dipolar interaction between layers, and that would be really interesting dynamics will be coming out, bilayer physics and so on. So we want to be able to generate the molecules in 2 dimensions and precisely control stable electrical fields, being able to implement evaporations and then thermalize the gas with dipolar collisions and so on. Try to see whether we can go below T over TF less than 0.1. So how do we, now we have this degenerate gas in 3D. How do we maintain that degeneracy in 2D? That's the first challenge. If you just subdivide, this is the molecular gas there in the dipolar trap. If you just load it into the science lattice, 2Ds, and the regular 1064 laser, and you have a 532 spacing, and you can see that it usually will divide into 25, 30 pancakes. We did that experiment also quite a while ago. And if this division process usually is not fully adiabatic in the sense that it's not a coherent dividing of the quantum gas, the T over TF increases in each layer. And typically, if you just go from here to there, the T over TF per layer would be going up to 5 or so. And if you try to do evaporation, that just seems to be a huge price to pay. So the idea is being, well, let's maybe take an intermediate step. Let's put a large space lattice in there. This large space lattice should be able to confine all the entire gas into a single pancake here first. And then you squeeze this pancake down and then subdivide it into a smaller science lattice in later. Ideally, you can go through the step one by one so that all the molecules can be squeezed into 1 or 2 pancakes. That's the idea. So we implemented this large spacing lattice, and as you can see, for rubidium atoms, it's very easy to see. This is the one layer of the large spacing lattice, and this by moving just the interference phase, you can move this lattice up and down. You can see 2 layers and so on. So you can load all the atoms into a single layer. The same thing can be done with potassium, and then you can do your molecular creation process. And indeed, we can actually create KRb molecules in a single layer. This is, again, a single layer of large spacing lattice, the 10 micron lattice. And in this single layer, at least T over TF is 0.4, so it's slightly larger, but not that much larger. We still have, fortunately, 50,000 molecules, a fairly large number of molecules in the single layer. So this is actually degenerate gas. It's not 2D yet. It's quasi 2D. The idea is the next step is really transfer to 104 layers of the actual science lattice where the spacing is a lot tighter. And spacing is not what's so important. Actually, what's important is the confinement. We want the confinement frequency to be really strong such that it's a truly 2D gas, not a quasi 2D. At the moment, we can squeeze the KRb radius to about 3.4 micron, which would mean if you just load that, it will be 7 layers of a 532 lattice. We'll see if we can squeeze this further or make this a little colder. So the next I want to talk about, once you have a single layer of molecules, the electrical field control will be key. This we actually put a lot of effort when we were designing and rebuilding the apparatus. As you can see now, all the electrodes are in vacuum. These 2 parallel plates are made out of transparent ITO plates, so the laser beams can go through them. And fortunately, they have survived after a few years of operation, even with watt-scale lasers going through with dipole traps and so on. We have 4 pairs of rods running from outside the vacuum coming in. This is actually we actually took this idea from our earlier OH experiment, where these rods can support both DC electrical field as well as microwave field. So altogether, if you put these fields together, you can actually use the voltage you apply to the 2 plates as well as individual control of the electrodes to create a spatially homogeneous electric field region here with a very small gradient. But if you wanted to introduce gradient, you can apply differential voltage between those rods. So that's the idea, is to be able to create reconfigurable electric field in space. And you can actually use rotational spectrometers. As I mentioned, those rods can carry directly with a microwave signal can propagate down the rods. And because you are in the so-called near field limit, the DC field that you calculate, you can use COMSOL to calculate the DC field. That's essentially also the distribution of the AC field. It's the same thing. Okay, so you can do rotational spectroscopy And you can actually move the molecules around. Concrete gave me a sign of 5-9 minutes. You can move the molecules around. You can actually do rotational spectra. As you're doing rotational spectroscopy, you just move them around, move the tip around, and you can map out the electric field throughout the trapping region. And here you can see that you're measuring out the E field curvature along the direction of the vertical as you move molecules up and down. And it agrees fairly well with the COMSOL modeling. And it here shows the picture that as we move to different locations by using different voltage we apply to the rods, you can actually see by the time you achieve this particular ratio of the voltage applied to the rod versus the parallel plates, you can move the molecules up and down over 100 micron distance or more than 200 micron distance, and electrical field remain to be fairly constant. So this is just our way of figuring out the environment of the way the electrical field is. We are just about to turn on electrical field control on all 4 rods to be able to tune both the electrical field and the gradient inside. And this will allow us to really be able to implement this evaporation in 2D. The idea being you apply electric field, the molecules gets polarized, and then you apply a little electrical field gradient in the transverse direction. You can basically tilt all the traps a little bit towards the sideways to force evaporation going on, while the molecules are colliding mostly through elastic collisions because they are dipolar collisions without inelastic loss because these are dipolar interactions in the long range. And then early on, John Bone and Gouvan Kumenair has calculated, for example, the elastic versus inelastic rate can exceed more than a factor of 100 once dipole moment exceeds 0.2, 0.25 device or so in a trap that we can now realize in the lab. So towards evaporative cooling, we have 50,000 molecules loaded in this optical lattice with a 40 kilohertz vertical trap frequency. And we can apply now much larger dipole moment with a large electric field. And indeed, we start to see the characterization of the loss in 2D. This is actually what theorists predicted as you apply, when the molecules are in 2D and you apply electric field, it gets dipole moment stronger and stronger. This is the loss rate I was describing earlier in 3D now, except this is the 2D loss rate. You can see it actually gets suppressed. And that's because as you go to larger field, the molecules gets more and more oriented, and their elastic collision gets stronger and stronger. But then it takes off again. This could be the process that we haven't really figured out completely, the transverse E field gradient to be controlling. It could be that we are already tilting it. Or in some sense, the evaporation is already happening, but we haven't controlled it. We needed to remove that completely and then gradually add onto that the gradient one by one to see how this controlled evaporation takes place. With that, I want to thank the current group members. Kyle, Will are both from Harvard. Thank you for sending them to Boulder. They have been amazing. And as I mentioned earlier, Luigi and Giacomo are I think in the audience. Junlu is from Wolfgang's group, just joined us as another postdoc from the Cambridge area. The previous group members, Jake Covey and Stephen Moses, that will help build this strontium, the KRB second generation machine. And Maria raised the theory support. And I also want to make a point that this work was recently featured as a science cover, along with Trump's new science advisor looks ahead. Thank you.
Great, so we have a couple minutes for questions. Wolfgang or Martin? Martin.
So, June, I'm sorry, but with this wonderful science cover, I have to poke you a little bit on the degeneracy of your Fermi. If you show the profiles of the K and the RB, and you might see 50% conversion in the center, but don't you need a global conversion that's very high to claim that you have degenerate Fermi gas in a harmonic trap, not just locally? And also, don't you need thermalization? Later, Anna Maria's theory requires T, the temperature.
Yes.
Do we have to have thermalization to claim degeneracy of the Fermi gas?
Yes, yes, absolutely. So the thermalization, if you say, how do you measure the thermalization? For the KRB molecule, we haven't. What we measure is the momentum distribution as they come out. and we measure the loss rate. As I explained to you last year, this is a two-step process, right? When potassium and rubidium come together to form Feshbach molecules, that process takes a few milliseconds, and the Feshbach molecule is actually happening in the thermal environment. And from Feshbach molecule to KRb, that uses the coherent laser transfer. And that indeed is very fast. And that whatever the momentum distribution of a KRb Feshbach molecule gets transferred into the ground state KRb molecules. So now the question you ask, well, now once the KRb molecules are in the ground state, what is the thermalization rate? That we don't.
Two questions. Right? The first one was even, don't you need global transfer efficiency, not just locally?
The global transfer
If you look
efficiency.
at the profile of the BEC, very slim, narrow, inside the big Fermi C,
Mm-hmm.
I will expect to only get good conversion in the very center where the BEC is, but nothing outside.
The conversion efficiency of 50% indeed is where the rubidium distribution is. That's right. And then once the rubidium distribution, this process of converting into KRb Feshbach molecules, which takes a few milliseconds to ramp through, right? So even though you started with a molecule which is in the center for the rubidium distribution, but there's a momentum that's going on. The Feshbach molecules are colliding with each other.
I doubt it.
The Feshbach molecules reach the thermal equilibrium. Anyways, but yeah, so you look at the distribution as you fly apart. That's how we can measure experimentally.
If you show the distribution, it would be very educational, I think. To
Yeah.
see again the potassium and the rubidium.
The distribution of, well, this one?
No.
This is experimentally measured in terms
Yes,
of.
that's a frozen in momentum distribution.
Yes.
From the potassium.
Here, of course, is you're talking about these distribution.
You have this beautiful Fermi sea of potassium, but you're only converting a small piece, a small sliver of it, and that piece is not even converted at 100% by less than 50%.
So we convert, for example, this part of the rubidium into the KRb, right? And then we remove all the potassium atoms out. So the KRb, if you look at let's see, we have this picture here. The KRb and the rubidium trap look, so you can say rubidium is initially distributed here, potassium distributed there, and then the potassium is distributed much wider because it's a Fermi sea. And when they convert it into the KRb molecules, the remaining potassium is all blown out. They are all gone, and what's left is just KRb molecules distributed here. And you can now it has changed the character. Rubidium started as a boson. KRb is a fermion, and that's just distributed in this dipole trap here.
But I guess, Drew, what Martin is asking, if I understand correctly, and if you would take hypothetically just potassium, the potassium distribution, you cut away spatially.
Yes, I understand, yeah.
And then you would remain with the same kind of momentum distribution, but we certainly would not claim that's a degenerate Fermi gas. Is that what you're
So maybe Wolfgang.
The question actually, which I wanted to ask you, is the following. If you would assume you have a perfect Fermi gas, perfect of KRb of Fermi molecules, but now by just having random losses, you eliminate 10% of the atoms. Your distribution would not change. I don't think your reaction rate would change because it's two-body collisions between particles in certain energy states. So you would have no observation whether your Fermi gas was, 100% T over TF of 0, or if you would have sandblasted out 10% of the molecules. Because if there are no collisions, you have just 10% overall loss, the momentum distribution looks the same, and I think since it's two-body collisions, which are only determined in P-wave collision, just means it depends on relative momenta, there would be no observable. And if you do the math, and if you say, I lose 5%, your Fermi-Dirac distribution looks exactly the same. But a T over TF of, let me try to do the math again. So if you have a T over TF of 0.2, it means your occupation at the bottom of the Fermi sea is higher than 99%. Because Fermi-Dirac distribution 1 over 1 plus e to the minus, e to the minus 5 means T over TF of 0.2 requires 99% occupation of the lowest state. T over TF of 0.3 probably means 5%. So therefore, I would say, since you are probably in your measurements not directly sensitive to the quantum occupation, only to the shape of the distribution,
Yeah.
a true claim for quantum degeneracy has to also address the question, what is the occupation number? And unless you have evaporative cooling or collisions which enhance occupation, occupation is related to entropy, is related to unitarity. You cannot increase, the fidelity of a quantum state in a unitary time evolution. My gut feeling is, if you want to say you have a degeneracy of better than 0.3, derived from the shape of the distribution, you also have to show that the quantum occupation of the lowest state exceeds 95%. And I think that would require, I'm not even talking about the global trappist Martin, I'm just talking about your best piece in the middle, where you have the lowest temperature, the highest density, the best conversion efficiency. But I think a quantum, a T over TF of 0.3, just calculate what is the occupation of the state at the bottom of the Fermi sea, has to exceed 95%. So unless you can show that your combined Fischbach-Stirrup efficiency maintains the fidelity, the phase space density, and you cannot have more than unity occupation in a Fermi gas, I think something is missing.
Well, that's why the atomic gas, the Fermi gas, the T over TF, when we create, say, KRb 0.3, the T over TF for potassium is 0.1. So it is, and if you lose by a factor of 10 atoms, that's how you increase the T over TF from 0.1 to 0.3.
I'm saying 0.3 has a fidelity per quantum state occupation of 95%.
Yeah.
And
So
if you start with potassium, which has a phase space density of 1, if you say a T equals 0, you would have 0 entropy. And if you have
well, no, it's not zero entropy, right? The efficiency is a certain amount, and that's the reason why the T over TF. If you had a 100% conversion efficiency, T over TF would not have changed. It would be 0.1, but it went from 0.1 to 0.3.
But that requires still to operate at 95% efficiency.
Sure.
Because a quantum occupation at the bottom of the Fermi sea of less than 95% would be incompatible with the T over TF of 0.3.
Yeah. So the question is, how do you measure that? I think you can measure by evaporation, as you say. That's something that indeed in the 2D gas we were trying to do.
You're claiming that in the center of the cloud you had a conversion efficiency of 95%.
No, center of the cloud for potassium. That we don't know, of course. How we cannot make that claim because we don't make that direct measurement. So the potassium is a majority, right? And the rubidium is in the middle. And indeed, as we showed, as you go to larger, when T over TF gets smaller and smaller, the conversion efficiency for the rubidium in the middle gets better and better. In fact, in the lattice experiment we did a couple of years ago, the conversion efficiency is 100%. When we had one rubidium, one potassium in a cell, and we were able to convert 100% of the potassium rubidium into KRb molecules. So in the middle, yes, I do believe the conversion efficiency is exceedingly high. You say, where is it direct experimental evidence? I can only point to the 2015 work when we actually put a dual insulators, put a potassium rubidium on top of each other, and efficiency is 100%, yes.
Okay, so let's take this debate later, and perhaps we need better detection, different kind of detection, in situ detection. So that's thanks, Jim, for the